we talk about significant figures. The first one, 1,000, has how many significant figures?
3. 1.
All right, I heard somebody say 3 and I heard somebody say 1. Give me an argument for either one.
1. 2 is actually.
Shh, raise your hand and tell me.
1.
Nina, why'd you say 1?
It's not 0.
Because any number that's not 0 is significant. Is there a decimal place at the end?
No. Well, actually there is.
Is there?
Well, no.
Is there one written?
No.
No. So the only number that's significant, Nina's very correct, is the 1. Right? Because 1 is a number between 1 and 9. All numbers between 1 and 9 are significant. 1, 2, 3, 4, 5, 6, 7, 8. 9. Alright? How about this one?
4. All of them. No,
4. All of them.
There's a debate.
4.
4.
We're consensus 4?
4, yes.
No, it's what?
It's 4. How?
The 1 is significant, right?
Is that a decimal point?
This is a decimal point. But is there a significant number in front of the decimal point?
No.
No. So zeros behind a decimal point, but not behind a significant number, are insignificant. Just like these zeros after a significant number and not between another significant number or a decimal point are also insignificant. Make sense? Right.
No.
Come back. Alright? What about up here?
All of them. 5.
5. They fall between after a significant number, after a decimal point, but before another significant number. Any zeros in between two significant numbers are significant. What about these?
4.
4. Right? After the decimal point, the first two are the 0 at the front, not, but the 2 in between the significant numbers, again, are significant. Right? Similarly, if I all of a sudden did this, how many do I have?
4.
4. Alright. That is significant figures. Going to ChemQuest 3. ChemQuest 3 deals with matter, right? We started off with the idea of physical change versus chemical change. We did a big lab on it.
Yep.
What indicates to us a physical change? What indicates a chemical change? Alan. Okay, physical change, the substance doesn't really change, is what you're trying to say? It only looks a little different. We'll see some appearance changes over there. But the substance doesn't really change. Same substance there. Shh, gentlemen, quiet. I want to be able to listen and hear everyone who talks and give them all detention. Same substance. But how would we see that and know that it was a change? What kinds of changes, or what do we see in a physical change?
Wait, like an example?
More like something that would tell me anytime I see this, I know it's just a physical change, not a chemical change.
And change it back to
Okay.
form.
If I could change it back,
Using the ladder.
I know I only made a physical change. So give me an example of that. What? Okay, coffee and sugar. I can separate the coffee and sugar, right? If I evaporate off the coffee, the sugar's left in the bottom of the pot. All right. What else?
Chalk.
What? Chalk. So that would be a change of what? What did we change that we knew it was just a physical change?
Still solid.
Fire shape.
The shape or size, right? When we ground the chalk up or we ripped the paper, all we did was change its shape and size. We didn't change the fundamental substance, right? Okay? Shape or size changes. And then what's our biggest example of changes that are physical in nature that we see on a regular basis? We see one currently because it's so cold.
Snow.
I don't know. So what's that change called? Change of what? What?
Physical change.
I know it's a physical change, but what are we changing? The what of matter?
The water.
State of matter.
The state of matter
I
changes.
said it first.
Nice job. Alright, those are all good examples or good rules of physical change. If we see it go from a solid to a liquid, we melt it, that's going to be physical. Shh. We're getting a little talkative. Chemical change.
Change of substance.
Okay, so the substance actually changes.
You can't change it back.
Unchange. Or
We can't easily change it back, right?
Oh, true.
And really, physically, we can separate these, right? If we mix them together, we can physically separate them. Here, we'd have to chemically do something, right, Oman? So what other things indicate? How do we know it when we see it? How do we know the substance actually changes when we see it?
smoke.
Okay, smoke would be an example. Smoke or gas is produced. What else? What else?
How about bubbles?
Bubbles would be the gas, right? It's a good example. In the liquid, we see a bubble form.
The color changes.
All right, color changes often indicate chemical change. What else?
You can smell that?
Well, smell would be another example of the gas, right? That's something that's permeated the air.
Look different.
Color change. No, we're forgetting a big one. Think about the match. The match, when you struck the match.
Fire.
Noise.
Well, so with fire, there could be noise or what? Noise,
Awkward thing.
Temperature.
heat produced, or sucked up, or
Feel.
what's the other thing you see when you light a?
Fire.
Friction.
Well, but the fire is an example of a
Gases.
Light.
light.
Oh, isn't it a gas though?
But all of these are basically what? Forms of
Fire.
energy.
Oh.
Alright? So when energy is either produced, or stored, right? Like when we melt ice, we're giving the energy to the water, but the water is still just coming to an equilibrium, right? Here, how many of you ever cracked a cold pack? Like an ice pack for your knee or something like that?
Yeah.
When you crack them, what is occurring is a chemical reaction that is taking energy from the environment to make that cold. It's then storing that energy in the bonds. Because remember, energy cannot be created or lost. It can only be changed. One change is to put it in a chemical bond as potential energy. When we burn the match, we're giving off the chemical energy that's stored in the bonds of the wood. Right? We're releasing it to the environment. That's the heat and light we see and feel. Does that make sense? Those are forms of energy very different than just, we're in boiling water, we're applying energy, right? But the energy is not coming from the substance itself. So that's why, that's when state of matter change is not an example of energy being released or stored. Does that make sense? Let's classify some matter. What are our two big ways to classify matter? Kind of the two broadest ways to classify matter. If we were scientists way back in the day, before we knew what atoms were and all that kind of stuff, what would be two easy ways to classify matter from Chem Quest 3? The two broadest ways to classify matter. That's why you're supposed to look at Chem Quest 3 time. Get your arms back.
Solid.
No, those are states of matter. Not a bad one, though.
Element and compound.
That's a little more specific than I want. Too broader than element and compound.
Elements and
Pure substances and
mixtures.
mixtures.
Yeah. Go back.
Gentlemen, control thyself. Mixtures. All right, pure substances, mixtures. Now, in pure substances, we can further now divide that group into what two things?
Elements.
Elements,
Compound.
compounds. So elements are
Oh. I found something.
elements are what?
No difference.
Atom.
There's just single atoms, right?
Oh.
Single atoms. Or single types of atoms. All right. And we know now that types of atoms are divided by how many protons they have. So all the elements have the same number of protons. Okay? Because there's different isotopes of every atom. Now compounds are made of,
Elements and mixtures.
so they're elements chemically bonded, right? And it could be 2, it could be 3, it could be 8 elements bonded together, right? It all depends on the substance that we're talking about, the pure substance. Now mixtures can be divided into two different groups. Homogeneous,
Oh, and heterogeneous.
all right? Homogeneous elements or homogeneous substances have how many phases?
4.
One phase, right? We can only see one thing when we look at it. Heterogeneous has how many phases?
8.
More than one.
Not 8.
More than Two.
More than one. All right. Now remember, we have to remember that phases of matter are different than states of matter. Because if we dissolve salt in water, is it homogeneous or heterogeneous? Homogeneous, because all we see is a single looking substance. But how many states of matter are in that substance? 2. The solid, the salt dissolved is still a solid, and then the liquid water that we dissolved it in, correct? So that is a homogeneous mixture. Because there's only one phase visible, even though there's 2 states of matter. Now, a heterogeneous mixture has more than 2 phases. Could be that they're the same, they're both liquids, right? Oil and water, right? You get the little bubbles. It's not going to stay in mixture very long, but while it's mixed, it's heterogeneous because not every part of it's equally spread out. But a better example of both, pay attention, would be Coca-Cola. So let's take a can of Coke, pop it open, pour it into a cup with ice. We see how many phases or states of matter when we do that? 3. We see a solid in the ice, a gas in the carbon dioxide bubbling up, and the liquid Coke, right? Or sugar water. All right? Now, let's pretend that same cup, we leave it for a week. The gas is all dissolved out. It's flat. The ice is melted. So now there's only one state of matter, right? It's all kind of liquid. The sugar in there is probably a solid, but that's the thing. Which one's homogeneous, which one's heterogeneous?
Second one's homogeneous. Second one is.
Second one's homogeneous. The first one is heterogeneous. Even if we just crack the Coke and it's fizzy, we're still in the heterogeneous mixture. All right? Any questions? I think we're running out of time, right?
Yeah.
So that's a pretty good spot through ChemQuest 3. We'll do the rest, a little bit tomorrow.
So you're gonna start putting